Okay, good evening, everyone. Can you hear me? We'll go through several experiments tonight, mainly with my laptop. So first, can you hear me? Okay, and can you see the screen?
Yes.
Okay, great. So let me start there. So really thankful to present and provide some information to you all regarding space weather and its effects on not only telecommunications, which I'm sure are direct interest to you, but also to many other systems. And so this will be sort of a whirlwind tour through several of these effects, with the emphasis on the explanation and the emphasis on providing sort of causes and effects as much as possible. So at any time, I would welcome any questions, any interruptions related to what you see and what you witness here. And so I'd like to, if you don't mind, start with a couple of questions on my own, just to make sure I understand a little better the audience. And I should say that I really wish I could be there. I was planning to be there. I think Ms. Leggero, who kindly prepared this event, knows about this already, but I was planning to be in a nearby location and then drive over to Mercer County in Sharon, PA, but it didn't work out, so I owe you all a visit. So, what space weather effects do you see? Do you see the typical absorptions and refractions and so on? Before I get into that, I'd like to hear a little more about what you've witnessed and what you'd like to hear about also.
Yeah. So we're very excited about the peak of the sunspot cycle, Dimitris, that is occurring now and through 2025. So we're very excited about that, and we'd like to learn about some of the solar storms and some of the interruptions in space weather caused by those storms due to the increased sunspots.
Great. Okay, very good. So we'll hear, I think I'll cover a couple of these points. Sounds good. Well, I have some more questions, but maybe I'll defer them until a later point in the presentation. Why don't we jump ahead? And so this will be a presentation of space weather effects, but also in the latter part of it, I will introduce some new missions and some new capabilities that NOAA is introducing in conjunction with NASA to monitor and record these effects and provide a causal chain from the sun to the Earth and their repercussions. So I think we've looked at this long enough. So space weather is a high priority for NOAA, as is terrestrial weather. The oft-repeated phrase is that we're planning for a space weather ready nation in addition to the standard NOAA weather ready nation. And space weather generates a number of effects, not only in communications, but also in astronaut and airline crew safety, in electric power grid disruptions, in long-distance undersea transoceanic cable communications, and many other in GPS and so on, and other effects that are still being, in a way, discovered and revealed. And therefore, as the nation's agency for monitoring all types of weather and providing its findings to the public and to the users, NOAA has the responsibility of developing and delivering this information. And there are several NOAA missions, NOAA and NASA, I should say, missions dedicated to this purpose. But several of them are sunsetting. They are reaching the end of their useful life, or they're well past the end of their originally planned life, and still they deliver very good results. So there's a need to replace those with new satellites, new instruments, and new even ground capabilities. So we'll go through some of those in the end. But let's see first where it all begins, right? Somebody already tends to jump forward. It all begins with the solar activity, and I think you already mentioned sunspots. This is what we see with a strong telescope in the visible part of the spectrum on the solar surface. These structures that are basically the breakup of magnetic field lines in the interior of the sun and their emergence as these darker, meaning cooler spots, the sunspots on the surface of the sun. These are arranged in pairs, very irregular pairs, but nevertheless eventually very symmetric in pairs in magnetic flux of what we call arbitrarily north and south. So north sort of featuring emerging magnetic field and south descending magnetic field. And when we visualize these with special types of light invisible to our eyes, ultraviolet and X-rays, we see that these magnetic field lines produce large loops or arcades that guide the plasma of the sun well above the surface. And when these arcades become unstable, then they lead to eruptions of several different kinds. Some of them are limited to the surface of the sun, and they are not dangerous to human activities, to humans and their activities. But the largest ones break off, and as we see here, these loops become unstable, and a large part of their material is released to the first to the outer atmosphere of the sun, and then it's carried out to eventually to the entire solar system. And this is what we call the solar wind, basically the emanation of the quiet plasma and also the more explosive structures of the plasma. And I should say, just to repeat, probably people are familiar with what plasma is. Plasma is the fourth state of matter, and familiar with, I think we're all familiar with the solid, liquid, and gaseous states of matter. But then when we go from one to the other and we eventually heat up a gas, then it leads to a plasma. It leads to a dissociation between ions and electrons, positive and negative charges, and that has repercussions on communications, as I'm sure it's familiar to those who have read the ARRL guidebook. So there is an effort to unlock, to reveal the mysteries of the sun, because understanding those, understanding what is hidden below the solar surface and just above it in the various atmospheric layers of the sun may lead to a better understanding of what happens near the Earth when these effects are manifested in the ionosphere and elsewhere. And this is a nice view of the upper atmosphere of the sun, the corona, as it's revealed by a NOAA mission, in this case GOES 17 and the SUVI instrument. So NOAA has capabilities of observing these instabilities and these structures as they're still very close to the sun before they really start their travel towards the Earth. Was there a question or a comment?
No, go ahead.
Okay, let's keep going. So, so again, this is a view. This is a very nice video that you can find online on YouTube or on NASA resources. This is one of these structures on the limb now of the sun. So this is in fact on the side. It's not at the top as it appears to be, but somebody rotated the picture so it appears very nicely at the close to the North Pole of the sun. In reality, it's somewhere on the side. And this is a loop. This is an arcade of loops which become unstable, and you will see them descend. And there's a lot of other activity, and I trust that you can see my cursor, right, moving around. There's a lot of other activity in the chromosphere and in other layers of the sun. So this is the base of the corona. and this is indicative of how large these structures are. You'll see the Earth's size in a few seconds. And somebody has put really nice music on that, so let's enjoy that. So I'll stop it here, but I think you can find the rest online, or you can send out an email. I can provide that, and you see how large the structures are, how impressive these storms are, and on the surface of our star, and how powerful they can be, reaching out even to the Earth's distance. Well, I think we can move on, right? And so let's move back. Here are some more examples of activity on the sun. There's a recently discovered effect that is called coronal rain. As it happens with many space weather effects, explanations and inspiration even for discovering them comes from terrestrial weather effects. So there is we have precipitation. We have terms like precipitation, for example, meaning precipitation of particles, not of snow and ice. We have convection, not of clouds, but of plasma. We have, in this case, rain of coronal material. This takes place at the base of these large structures, similar to some that I showed earlier. These are now much more left, these structures here are called helmet streamers. They extend out several solar radii long. And at the base of these streamers, there's material that descends, that cools down from further up, from the top of the streamers, and then descends down and falls on the surface of the sun. And so this is an open research item. It doesn't have a lot of space weather effects. It's more peaceful, more benign effect, but still it's one of the mysteries of the near surface solar activity that solar scientists aim to resolve. Now let's go further out from the sun, from our star, and we see this schematic, this nice artist's concept of the solar wind, that material that, like steam from a pot, from a kettle, leaves the surface, leaves the boundary of the of the rising, the boiling sun, and then goes out, as if it goes into a room. In this case, it fills out the entire solar system, and it defines the solar system. We call that eventually the heliosphere, the place where the solar wind stops, where it really breaks, where it's decelerating, is really where it collides with similar stellar winds from other stars, and that really defines the edge of our solar system. Not our planets, not the comets, not the other exotic structures that are rotating around the sun, but that very dilute, very imperceptible plasma material that starts its travel on the surface of the sun. And then let me replay this, and if I can with this cursor. And so you'll see that the artist, in addition to showing the invisible boundary here around the Earth, towards, at this point, shows what the boundary is due to. The boundary is due to, of course, the magnetic field of the Earth, invisible to us, but perceptible through our measurements from spacecraft, which provides a bulwark, basically a resistance, a wave breaker, if you like, to this onslaught of material from the sun, and protects us, as it were. It protects us from certain energetic particles, and also from the arrival of the plasma, which on other planets does reach the surface. For example, from Mercury or in Mars, and Mercury has a much smaller magnetic field, magnetic cavity called the magnetosphere. Mars does not have any such magnetic protection, and so the solar material arrives on its surface directly. Um, and so that gives you another view of another space weather environment different from the sun. This is a planetary space weather environment which strongly interacts, which strongly interplays with the changes that happen on the solar surface, the solar atmosphere. And so the rubric there says, the title says that the solar wind and its transient structures produce space weather at Earth. What does that mean? Well, the solar wind is just really anything that flows outwards from the sun. But really, when we say that, we really mean either the slow solar wind, the slow plasma, outward motion, or sometimes the fast solar wind, but still formless. In addition to these types of formless solar material, we have these structures that I'll talk about later, which are the explosive remnants, the ejecta, as they're called, or more technically, the coronal mass ejections, that are transient. They don't happen all the time. They happen when these loops that we saw explode and release their heavier material outward. So we have this combination of effects. We have the solar wind blowing all the time, sometimes more slowly, sometimes more rapidly. And then we have these heavier structures, heavier again, not relative to our own terrestrial atmosphere. They're still very dilute, but still heavier than the ordinary, the run-of-the-mill solar wind that buffets the Earth. And so let's take a look. Again, that's a model. This is not now an artist concept. There are artist concepts and they're useful, but now also there are models that become more and more detailed and user-friendly. And this is our planet's magnetosphere, which is a really dynamic system. It also has its own internal dynamics, but it's also compressed. It also changes shape and direction. It's very strongly compressed in the front, in the nose, as we call it colloquially, and it's very extended in the night side, in the tail. Again, these are technical terms, really, the nose and the tail. And you can see how much the magnetic field lines, these are the lines shown here in the terrestrial realm, and also the magnetic field lines in the interplanetary realm, how much they change even under these idealized model conditions. And of course, now this is a relatively dated simulation, but it's kind of nice to show this in a simplified manner. There are much more sophisticated simulations that are more complex. So we're going now from the sun towards the Earth, and this is a more familiar environment for those who are dealing with radio propagation, with absorption, in other words, radio enthusiasts and other radio wave users, satellite users, ground users, and so on. And so let's go through the more innocuous effects, the more benign space weather. On the left, we have a view from the space station, showing the various types of, again, plasma environments above the surface. We're now much closer to the surface of the Earth than before when we were looking at the magnetosphere. And these are the various layers of the ionosphere, which actually extends much further above. This is the air glow. We see city lights. We see some lightning. And we also see there was some lightning flash there, light blue or white. And then we see the aurora as the space station goes through the northern or southern latitudes. And the aurora is very dynamic, of course, in its own right. Very different views depending on the scale. Here's a more placid appearing view above a lake, seen from the ground. This is the theta aurora, looking like a circle with a bar in the middle of it. One of the earliest pictures, one of the classic NASA photographs of the aurora as it's seen from from a satellite. And of course, to its right is the air glow, the response of the atmosphere and the atmosphere to UV light, to sunlight and UV light. And so auroral displays are manifestations of space weather. They come in a wide variety of structures, from smaller arcs and their subdivisions to large-scale formations like this global size, this planet-sized, essentially, theta aurora. And then, of course, there are many, many different wavelengths, and for radio applications, there are also many different radio impacts. And so let's review again a little bit the solar sources for the space weather effects. In recent storms that we had this year, and also very active events last year, 2023, we had a combination of effects. We didn't have just one solar effect producing another terrestrial effect, but we had a combination of solar near surface and atmospheric effects producing a more deleterious, a more complicated effect at Earth's location. So here we have basically a trifecta. We had a combination of fast solar wind from a so-called coronal hole. This appears dark because in this particular wavelength, in UV, it has a lower emission. So even though it's there and it's active, it appears less visible, appears dark here. So from that emanates a very fast solar wind. But in addition to that, we had coronal loops like the ones that we see here. And of course, we're in March. That means equinox, and that means the location of the Earth is, and the magnetosphere of the Earth is more prone to disturbances happening at the equatorial plane of the sun, because then the equatorial plane of the sun and the ecliptic plane on which the Earth travels are more aligned during equinoxes. So we had a seasonal effect, the equinox, being combined with these more transient effects on the surface of the sun. And this led to the very strong storms that we saw in March 2023 and later that year, further away from equinox, of course. And so here are some very nice, since we just talked about the aurora, let's look at some of the auroral forms, which perhaps make us think of all the complexity in nature, at least in the plasma renderings that we see in nature, and also these plasma structures in the ionosphere are somewhat reminiscent of all the complexity that we saw in the magnetosphere further away, and even in the sun. Nature is very, very complex. So this is a view of somebody's porch in Edmonton, Canada, CA, Canada there. This is a special touristic location in the northern latitudes where somebody can rent a cabin with an open window, part of its dome, and they do not have to stay outside to enjoy the polar lights. This is a view from, again, the March 2023 storms that somebody took with their cell phone and posted on social media. I think Instagram, one of many, many different pictures. This was a storm that they took a snapshot of as they were traveling from New York to Minnesota. You can see there how close to the human experience these effects can be with our capability to travel high above the atmosphere and take pictures. This is a picture that I like. This is somebody's view of their kids' first aurora, and as we had the opportunity in the last couple of years, many kids and many of us were able to witness their first manifestation of this celestial effect. And so you can imagine what impression that would have in to young eyes. And this is another view of how strong these storms were. So when a magnetic storm, when a magnetospheric storm, we talked about the magnetosphere, and its storms are called geomagnetic storms. And when these storms become very strong, and of course they are accompanied by ionospheric storms that have the radio effects very much pronounced. But here the point is that this photograph was taken in Phoenix, Arizona, so very far south, very far away from the North Pole or the periphery of the North Pole, where you usually have the auroral ring. And so when we have very strong storm conditions, that part of the activity descends to lower and lower latitudes, and in this case, it was visible in early in the day in Phoenix and many other locations in that storm and in many other storms. And this is a view because I live in the Washington area. This is a view that that circulate also in social media. So I selected that from the Shenandoah Valley, somewhere in Virginia, west of Washington. Now let's move a little bit to more detrimental effects for space weather, and these are the ones that really motivate NOAA planners, scientists, engineers to really design these missions, build them, test them, and fly them. And so we've had several effects over the years where these conditions that really started out very far from here at the surface of our star made their way through the magnetosphere, through the ionosphere, and really had effects on the ground. And they drew very strong currents on the ground just below the surface. These are called geomagnetically induced currents. That's the technical term. And those strong currents that flow in the Earth's crust can interact with human-made structures on the ground that are very long conductors, essentially, whether they are railroad lines, railroad tracks, or telegraph lines in the 1800s, for example, or in these more modern days, they're electric power grid conduits. They can lead to interesting effects historically and or also more recently. In this case, they led to transformer damages in the vicinity of Quebec City and also in New Jersey. Hydro-Quebec, which was the hydroelectric company responsible for electrification of the area, lost electric power for 9 hours. And several other effects have been reported since then, not only in the US, but also in other countries, all the way down in South Africa. Again, we have the mark of the storm, not just at high latitudes where the auroras take place, but also when the storms are very strong at more and more southern latitudes close to the equator. And this is from a recent study with a historic storm where we didn't really have advanced models, we just had measurements. But these were the data that were used to drive the 2009 power grid. And we see the usual sort of pressure points, the sensitive areas that have to do with the conductivity of the ground, not the conductivity of the ionosphere only, but also the conductivity of the Earth's crust, which can allow these currents to flow more strongly in one direction in some regions than others. And so the Northeast and parts of the Midwest are more prone to these damages, and also the Northwest is also prone based on the telluric resistance, the crust resistance. Another effect is that humans experience, and these are astronauts, particularly in the space station these days, and with the Artemis program that NASA is planning to develop also on the Moon and later on Mars. So these disruptions the space weather changes can impact those humans flying far from the Earth's protective magnetic field. Of course, the ISS is still in the magnetic field, but it's not as close as other locations closer to the ground. And then when airline crews and passengers fly over the poles where the atmospheric effects are stronger, and the magnetic field also is stronger because it's concentrated close to the poles. There are ways that energetic particles from the sun can flow down these pathways and and their flux increases to the point where it poses health hazards to airline crews, for example, which who fly frequently over those regions. So with the advent of the polar routes that were designed for financial reasons, for optimizing travel times for airlines, came more exposure to airline crews. And last year we had a law case in which a court awarded damages to the family of an airline steward who died from a prolonged exposure to solar and galactic particle fluxes. So let's talk a little bit about communications as another important effect. So I'll show some slides taken from a recent presentation by Mark McAllister, who's with the Department of Homeland Security. And there is a significant attention paid there for space weather effect on communications. And I will just quickly go through some of these effects, which I think are known to several of you. So NOAA distinguishes between three different types of disturbances as major items of disruption. And so we distinguish between the geomagnetic storms, we have the G scale, we have solar radiation storms, which are fluxes of particles like the ones I just described from the sun or even from further away from the galaxy. And the particles are strong enough to go through the protective magnetic field of the Earth and cause these health hazards to airlines. At the same time, they can also increase ionization, and they can increase the absorption near the poles. So we have the polar cap absorption for stations or for systems that are at high latitudes. And then we have the solar flare effects, which are measured in the R scale, where we have X-rays contributing to ionization of the ionosphere, of the atmosphere, production of stronger ionospheric densities, and that increases also the absorption of the radio signals, and that can produce disturbances that last for a while. So with these three effects, there are manifestations in all the ionospheric layers during the daytime. And then during the nighttime, since we don't have a direct exposure to the sun, and it's either it's particles or it's X-rays, the only effect, which is still important, is the effect of the geomagnetic storm, which has a global footprint. As I mentioned earlier, these are global disturbances, so they reach not only on the day side, but also during the night. And so this is a view. Let me ask, who has seen this type of graph? Quick poll here. Nobody has seen this graph?
Yes, we've seen that before. Go ahead.
Good. So what is it? Let me put you on the spot, whoever asked, answer the question.
No, you can go ahead and continue, Dimitris.
Okay, I think do we have an hour or do we have less time?
We have a little less time than that.
How much time do I have?
There are 30 minutes, but go ahead.
Oh, okay, I'll start dropping up then. So so we have these effects that indicate the X-ray effects, and also we have the polar cap absorption at the high latitudes. Let's move forward, and these are renderings of the solar radiation storm effects and the geomagnetic storm. And I'll leave the satellite effects so that we can go forward. So with the planning that takes place in NOAA, we have three programmatic functions. One is taking place for observations and measurements, and the Space Weather Observations Office, where I work, is responsible for that. Then there is a branch that's responsible for monitoring and forecasting, and eventually there's a need for the data to be processed, archived, and maintained. And so these are implemented in different offices of NOAA. So the NOAA Space Weather Prediction Center is the most well-known branch of or office within NOAA that's responsible for issuing nowcasts and forecasts, and other warnings and watches for conditions related to space weather. And in addition to that, there is a need for missions to gather the data to feed into either models or to forecast charts that forecasters can review and evaluate. So our office here in Space Weather Observations is responsible for designing, building, and flying missions such as and instruments such as the compact coronagraph that we flew on the GOES-U satellite, and then the SWIFO Lagrange 1 observatory, which will be launched next year. So I'll go through them to review the major points here. So for mission 1, we have our SICOR 1 coronagraph telescope on board the GOES-19 satellite. This is a mission that has started. It was launched in June of this year. And the satellite is in geostationary orbit around the Earth, with SICOR being one of the instruments in its solar pointing platform. SICOR, as well as other solar viewing instruments, are monitoring the sun 24 hours a day, except when the spacecraft is in eclipse, close to the equinox. And they're providing views of the coronal activity throughout their observations. And the data come down from that geostationary platform to the ground to several redundant stations, and then they're processed and provided to users. There are some interesting effects having to do with the fact that there are eclipses close to equinox. So at that time, the solar viewing instruments do not cover that activity, and so we have a second satellite providing that capability. This is a view from the launch that took place on June 25th, 2024, from Kennedy Space Center. These flights are organized and executed in conjunction with NASA plans and guidelines. And the mission has been successful in placing the satellite in orbit, and our coronagraph at the stage where it is on.
Audio is breaking.
Go forward. So now in mission 2. I'm sorry?
Go ahead. Your audio was breaking up, but I think it's better now.
Okay. So with the second mission, we're planning for a more ambitious launch, placing a satellite at the libration point on the left and Earth on the right. This is an gravitational equilibrium, which
we're
will
losing.
allow our satellite to monitor and measurement also will be able to measure the solar wind and magnetic field. So say it again. Is there a problem with audio?
Yeah, go ahead.
Okay. That mission is planned for spring 2025, and it will be a ride share with NASA's IMAP mission. They both will operate from the Lagrange 1 point. These are the instruments that we've built and we have integrated on the spacecraft. So in this case, we have launched the SECOR-1, and we have integrated the other four instruments on the Trefoil-1. These are high heritage instruments from NASA flights, and they're going to be used operationally continuously through the life of these missions. So in passing, I will mention that one of our instruments, SWIPS, will measure the solar wind, both the density and its velocity as that solar wind passes in the Earth's vicinity. A second instrument will measure the particles that emanate from the sun and can obliterate the field of view of coronagraphs such as this one, and also endanger humans in space. So these particles will be used both for forecasting, for alerting purposes, and also for models and other applications. And also an important instrument is the magnetometer. The solar wind carries a magnetic field that starts out in the solar wind on the sun, and the magnetic field, together with the plasma measurements, are providing a more complete description of the plasma environment in the vicinity of the spacecraft. The status of the second mission is that all instruments have been integrated and tested. That was back in April 2024, and through the summer we've been testing these instruments on the spacecraft, and they've successfully passed that stage. Now we're planning for the launch, which again is for spring 2025. On the ground segment, we have set up all our ground antennas, and I'll show a graphic on that. And we have we've come to agreements with various international partner organizations to provide additional coverage. We'll skip this slide. Here is a view of how the various stations on the Earth's surface will track the footprint of the satellite as it moves from east to west. So you will be able to see how different stations pick up the signal, and they continuously cover the downlink transmission of the data. So we don't have any data gaps from the spacecraft, either in images or in data. And the products that that we're planning for are images of these coronal mass ejections, as seen in this historical explosion from November 2023, and also time series data that will power the NOAA models. Here I have some links to space weather data and images. So at the end of the talk, I will provide those in the chat window for people who are interested in gathering more information. And then the data for other will be placed on long-term storage, where users such as scientists and modelers will be able to collect them and use them to develop their models further. So we're getting ready for Solar Max, which will take place in July of next year. And this will, as we progress there, the sun has been changing its behavior radically. This is a view of the quiet sun on the left, and then a more active sun 2 years later as it approached solar maximum. Solar activity has picked up, and several spacecraft, in addition to ours, but mainly by NASA and NOAA, have been monitoring this activity. Several of them are equipped with coronagraphs, and they will be providing their data, not necessarily in real time like ours, but also in more delayed conditions. But scientists are interested in both types of effects. And as a view in closing of what comes next, NOAA is designing the Space Weather Next program to build such platforms not only at the Lagrangian point shown here or at the geostationary orbit, but also at distant locations like Lagrange point 4 with agreements with international partners, and Lagrange point 5 in coordination with ESA, that will give us a more global view both from the Earth's vicinity and also distant places further out in the solar system of these disturbances as they emerge from the sun and they arrive at the Earth's vicinity. So in closing, this is a reminder that all this activity takes place on the solar surface. We're exploring still the causes of space weather on Earth, but we have a good grasp on the causal chain as our models become more and more accurate and more prediction oriented. So in summary, NOAA's goal is one of not only monitoring space weather, but also modeling and forecasting it, and then providing this information, which is as accurate as possible, to key stakeholders, that is industry, other government branches, various types of users, and the broader public for education and also for a wide range of applications. So with that, and with apologies for going over time, I'd like to thank you for your attention.
Thank you very much, Dimitris.
You're welcome. If we have time for any questions, I would be happy to entertain them. Otherwise, I will stop here.
Okay, and Corey has recorded this, so if you want to go back and play it again, Corey will post this up on the website, so you'll have that as well. And Dimitris, we thank you for your research and your science, and thank you for giving us your time, your own personal time here this evening. That was quite kind of you, and you are always welcome to attend our meeting. We would welcome you here to have discussions one-on-one with our members. But thank you again, Dimitris.
You're very welcome. I enjoyed it.
Okay.
I'll stop here.
And thank you, Corey, and thanks to all on Zoom. And we will be up at the Mexican restaurant La Isla for dinner if you were so inclined. We'll be up there here after the meeting. So 73, and we'll see you at Buell Day, W3 Bravo.